have PST, mean primary settling tank, it will flow into trickling filters and secondary settling tank. That's it. Only in one run. Comparing to the high rate with a recirculation, so you can see, yeah, from the secondary tank, which is the SST, it will come back to the primary tank. Yeah, so this is what I mean by recirculation. So the advantages of employing the trickling filters is very efficient, yeah, for the removal of BOD and ammonia. Just now RBC is ammonia, nitrogen and nitrogen can. So use a minimal amount of power, yeah. Disadvantages: power breakdown, yeah, cause gravel bed dry, bacteria died and smelly condition. So these are the major disadvantages of employing the trickling filters. Yeah. Apart from monitoring, yeah, the colors of the slime, we can also monitor the pH, the concentration of the waste, the concentration of the oxygen. Yes, because these are the common parameters to be monitored. Yeah, whenever you run a biological system. Okay. So the expected pH is around 7 for the OD removal condition. For ammonia, sometimes the pH is higher, about 8. Yeah? So that's why whenever you have high concentration of protein in your sample, definitely you will get higher pH, yeah? Because whenever a higher protein concentration can cause higher ammonia production, thus increase the pH value. Okay, recirculation. Okay, recirculation in a trickling filters is a system where we recirculate the effluent. Okay, we have to recirculate the effluent for what? To reduce the organic loading, to improve the sloughing, to reduce the odors, and to reduce or eliminate filter by a bonding problem. Okay, so we would like to promote more activities. That's why we employ recirculation in a trickling filter system. On top of that, yeah, because trickling filters normally exist as a one single unit. It's not in a series of the train or drum like RBC. That's why it's good to apply a recirculation. Yeah. Uh, so we need to so in this example, we have two examples. First, to calculate the total flow. Second, to calculate the organic loading. You have calculate. I have shared with you just now on the example of organic loading. Now let's see the total flow. Yeah, there are two examples here. First, the total. I would like to share with you how recirculation rate can influence the total flow. Yeah, for example, the formula below can be used. Inflow times recirculation rate plus 1. Yeah, so case 1, yeah, the trickling filter is currently operating with a recirculation rate of 1.5. Yeah, so calculate the total flow. You calculate the total flow whenever the influent is equal to 4.25 megagallon per day. In second case, the influent flow is 72 mgd, but the recirculation is only 0.009. I would like you to see the difference, to compare in terms of the answer. You can see here, when you solve for this equation for the case 1, to calculate for the total flow, the recirculation is 1.5. Yeah, you can see the actual flow is 4.25. When you employ recirculation, the total flow will become 10.63. But in case 2, the total flow is 72 mgd. But since the recirculation rate is very small, there is not much different, from the original flow to the total flow. So these are the major difference whenever we employ the recirculation. Okay, so I think that's all. Not yet for today, but we still have the Mbbr. Okay, let's watch a short video on the Mbbr. So after this, we can continue with the calculation on how to design the system. Yeah?
The ideal Mbbr is a state-of-the-art fixed film biological process used in municipal and industrial wastewater treatment for BOD and COD removal, as well as nitrification and denitrification. One concept of applying the moving bed biofilm reactor, or Mbbr process, is for industrial pretreatment, which shaves off 60 to 80% of the influent BOD, all while lowering the loads heading to publicly owned treatment works, or POTWs. The Mbbr process is a 100% flow-through process, meaning the flow rate of the reactor effluent is the same as the influent coming into the reactor. In industrial applications, the water level, or side water depth, is maintained by the gooseneck effluent piping on the outside of the tank. This allows for the reactor to reach its maximum retention time, and for complete submergence of the media retention screen. The inside of a reactor does not have moving parts that will require maintenance. First and foremost, each reactor will have specially designed, submerged, freely moving biomedia, providing abundant surface for bacteria, or biofilm, to grow and thrive. Bacteria will grow on the media in multiple layers, allowing the Mbbr to be very robust and self-regulating. If an event were to occur, such as a giant pH swing, the media will not lose all of the layers of the bacteria, giving the Mbbr the opportunity to recover much quicker than other processes. The bacteria digests the organics in the waste stream and converts the soluble material into biomass, which will be removed downstream by a solid separation system. An Mbbr for BOD and/or COD removal, or nitrification, is an aerobic system, meaning oxygen is introduced into the reactor to allow bacteria growth. Oxygen is brought into the tank by having blowers send air through stainless steel aeration manifolds. The aeration manifolds are strategically placed inside the tank to have even coverage throughout the entire volume of the reactor, and to provide the necessary mixing for maximum treatment during the reactor's retention time. Stainless steel media retention screens are placed on the effluent flange, as well as the overflow and drain flange, to prevent the media from escaping the reactor. The continuous movement created by the media in the tank scours the screen and minimizes any deposition of solids which could create any head loss. Even though the Mbbr is robust and can handle many load variations, there can be times, especially in industrial applications, where additional nutrients will need to be supplied. In those cases, an ammonia or phosphorus source may be needed to maintain the proper ratio for the bacteria to thrive and remove the desired amount of soluble organics. Anti-foam may also be needed if the waste stream tends to produce foam. The World Water Works ideal Mbbr process provides the smallest footprint biological system. For industrial clients, World Water Works specializes in cost-effective pre-treatment systems, such as combining the Mbbr with its own ideal DAP system. The design is simple to operate, at a low capital cost, all while staying tolerant of both load swings and temporary load deprivation. We at World Water Works are ensuring our wastewater treatment systems meet today's challenges while preparing for tomorrow's needs.
Okay, so these are the moving bed bioreactor system. Yeah, moving bed bioreactor system, where a system. This is okay. So the moving bed bioreactor system is more or less a system like RBC and trickling filters. The only difference is the filter media are moving, yeah, within the tank. Yeah, the filter media in the RBC as well as the trickling filters, they stay within one place, not moving. But in the moving bed bioreactor, the filter media, they are swimming, yeah, within the in the water tank. They are moving, yeah, they are moving. So that in some cases, yeah, it can have a better removal. Why? Because the movement of the filter media within the tank can improve a better contact between the microbes, the food, the waste, as well as the oxygen. And again, the Mbbr system is an aerobic system. Okay.
Saya duduk. RM200. Saya dah close dah position long saya.
It is now 8:03. Talk about daily load and loading rate. We're talking about BOD. So how much?
Okay. Okay. All right. Okay. We can watch another video. Oh, the video is no longer available. Okay, the video is no longer available. Okay. Alright, then we shall continue with the Mbbr system. Okay, so basically these are the process of a fixed film process of an attached growth process where the filter media is floating and free to move within the tank. Okay, so these are the actual photo of the media. Let's say we have this. They are made of plastic. The diameter of this media is about 1 centimeter. Very small. Okay, so these are the photo of the filter media after few months of operation. You can see the microbes get intact with the media, so that they stay within the media. So this is what do we want. This is what do we call as biofilm. Layer of biofilm, the proof of having the microorganism within the media. So we provide a house, we provide a good space, a small space for the microbes so that they will feel secure to stay within the media. Okay, so this is actually the spirit of having the filter system, but employing the Mbbr will promote more contact. It will promote more contact between water, the wastewater, as well as the microbes and also the oxygen. Okay. So these are the actual flow, the actual diagram of the Mbbr. Still, we have to use the screening process, the grid removal process. But employing this system, we are going to we can combine the aeration tank, the aeration tank with the primary tank, and this is the secondary clarifier. Okay, still need a sludge treatment. Okay, so how does the system works? The pieces of the biofilm will provide a better solution for the removing of waste in the water. So currently we do have one in Langkawi Island, but that one is operated still under pilot scale. But they are moving forward to use this system for the treatment of domestic wastewater. But soon they are going to use for the treatment of food and beverage industry wastewater. So the the advantages of this system is a perfect wastewater solution for space constraint, easy to use for inexperienced plant operators, require require little maintenance and resistant to shock load. So this one is more robust. The system is more robust because they are resistant to shock load. This is due to high population of microorganisms within the media and the better surface area. All right. Okay. So So we have one more calculation. We have two more calculation to cover today. Okay, all right. This also the uh, these are also the revision. Yeah, we have covered this in during in environmental engineering subject. But the reason why I included here because you need to use this calculation in your project. Okay. All right. Compare the area requirement for conventional trickling filters with loading of 0.1 kg BOD per meter cube day and conventional activated sludge with loading of 0.56 BOD per meter cube day. Okay. So in this case, we are comparing the area required based on different loading rate. Yeah. So in this question, you need to design for the trickling filters as well as you need to find the area required for the trickling filters as well as the area required for the aeration tank in the conventional activated sludge process. Okay, so you are given the information. First is the information on the loading rate, which is 0.1 for the trickling filters and 0.56 for the for the aeration process. And you are also being given the concentration of the BOD and also the population as well as the average flow of the wastewater LPD, is uh, liter per person per day, or sometimes can also be written as L per LCD, liter per capita per day. So these are the amount of the wastewater produced, average flow average flow of the wastewater produced per person per day. In this question, these values are given 200. If it is not given, then you can take as 2 to 5. I repeat, in this question, this value is given, so you have to use this value. Unless otherwise stated, then you have to use the value of 2 to 5. Okay. Take filter depth and area of the aeration tank is 2 meters and 3 meters for the, take filter depth. This is the filter depth. This is the depth for the trickling filters, which is 2 meters, and 3 meters is the depth for the aeration tank. Okay, and then after you have complete this, after you have you have calculated the area required, then you consider the area required if the primary tank has removed 30% of the BOD. Okay, all right. First, how to solve this question? You have to calculate the flow rate. How to calculate the flow rate? You are given the population as well as the average flow, just times lah. So you will get about this value. Then you calculate the BOD mass. BOD mass is equal to BOD times Q. So BOD concentration is given as 250 milligram per liter times Q calculated earlier. So you will get BOD mass equal to 1,500 kg per day. Okay, this is for the trickling filters. Then you can calculate for the volume. BOD mass is given as 15 kg per day. BOD loading is given in the question. So that you will get the volume. The volume is 15,000 meter cube. So these are the volume. To get the area, then volume equal to A times D. D is given as 2. So the volume, the area required for a trickling filters is 7,500 meters squared. Okay, next, compare to the aeration tank. And this is only the aeration tank. Logically, the activated sludge system will require larger area as compared to the trickling filters. But now we are only comparing the heart of the process, which is the aeration tank and the trickling filters. Okay, volume the same steps actually, since we have the same BOD mass, but you need to change the BOD load, because the BOD load given for the aeration tank is 0.56 kg per meters cube day. So you will get the volume about 2,680. You can calculate for the area, and the area is 893. Okay, 893 area required for the aeration tank. Okay, next question is mentioned that if the primary tanks remove 35% of the BOD, then what happened? Okay, then what happened if 35%? Logically, logically in any of the system, there should be a primary and preliminary process. It cannot suddenly the biological process. It's almost impossible. Why? Because the system will be overloaded. Yeah. So in this case, we are considering 35% of the BOD has been removed during primary and also preliminary process. So what to do if you are to consider this removal rate? So um, again, the information given to you is 35% BOD removed. So 100 minus 35 is equal to 65%. So this is going to be the applied BOD. Yeah. So the applied BOD 65 over 100 times the concentration of the actual BOD, which is given in the question. So you will get 162.5. These are the concentration of the BOD to be treated, to be used in the following equation in order to calculate for the area. Yeah. So in the previous example, we use 6 times 10 to the power of 6 liter per day times 250. So in this case, since we have considered the BOD removal, so that of 35%, so that we have to use the new BOD. Okay, then the steps are more or less the same. You can get the BOD mass. So BOD mass divided by the BOD loading. Yeah, so you will get about 9750. So in this case, in this example, I have only solved for the trickling filters. Basically, the area required is about 4875. Yeah, comparing with a system without comparing with the system without any removal during primary stage is about 7,500 meter squared. But in this case, after we have considered the removal rate, the size, the area required is only 4,875 meter squared. Okay. Alright. So these are the examples. Do you have any question for this calculation? Any questions?
No, doctor.
Okay, great. Yeah, so you need this is already covered in the previous years, but you need to use this calculation later to complete your project. You have only one project, for this course. I will pass through the project after the test one. Okay, next is on the calculation to calculate for the design for the trickling filters as well as the RBC. Okay, these are trickling filter loading. Yeah, a 10 meters diameter single stage trickling filters contains conventional cross flow plastic packing at a depth of 6.1 meters. Okay, this example is not too long. The solution is not too long, but the problem is you have to refer to few tables before you can complete. Before you can solve this equation. Okay, before you can solve this equation, you have to refer to few tables. But the solution, the step is not many lah. Yeah. Okay, you can read the question first. Okay, yeah, a 10-meter diameter single stack trickling filters. Yeah, the depth is about 6.1 meters. The primary effluent with a characteristic given below is applied to the filter. Yeah, so calculate the volumetric BOD and total nitrogen loading. Yeah, I remove K because TKN is total held down nitrogen. Yeah, some people they use TKN, yeah, but I prefer to use as total nitrogen because to calculate total nitrogen we use TKN. We use TKN. Yeah. First calculate what is the volumetric BOD and total nitrogen loading. Then what is the specific total nitrogen loading. Then what is approximate BOD removal efficiency at 20%, and identify whether nitrification can be expected or not. Okay, why? Because in the trickling filters, we have to monitor this. Yeah, we have to monitor the nitrification based on the nitrogen concentration as well as the BOD. Okay, you are given in this table the characteristic of the wastewater. Yeah, the flow rate is 4,000, the BOD is 1,200, the TSS is 80%, the total nitrogen is 25%. Yeah, all of them are in the unit of gram per meter cube, which is also milligram per liter, except the flow rate. Okay, first, determine the volume, yeah, of the trickling filter packing material. Yeah, volume is equal to A times D. Everyone know this. So A is since this is you have to use the formula for circle to calculate for the area. So A D is 10 meter squared is given in the question. Divided by 4 is the part of the equation, so you will get area equal to 78.5 meters squared. Yeah, so that the volume 78 times 6.1. Yeah, 6.1 is given lah. Yeah, okay. Okay, 6.1 is given. Yeah, so now you can get the volume. Yeah, next step is to calculate the BOD loading. Yeah, to calculate the BOD loading, yeah, is equal to QS naught over V. Okay, you need to calculate for BOD loading as well as the total nitrogen loading. Okay, so for the BOD loading, Q is equal to 4,000 is given. 1,120 is given in the question, the S naught. And what is S naught? S naught is the BOD. Okay, already mentioned just now. The BOD can also sometimes known as the, sometimes can also be represented by the S naught. Yeah, and 1 kg, this is only the unit conversion, and 479 meter cube is the volume. You solve for this equation, you will get 1 kg per meter cube day. Yeah. Next, you have to determine the total nitrogen loading. Yeah, right. Total nitrogen loading rate, you still use more or less the same formula, but you have to change the S naught. Yeah. So in this case, just now, when you calculate for the BOD, you use 120. So now, whenever you calculate for the nitrogen, then you have to use 25. Okay, you have to use 25. So here is 25. So that this is the unit conversion. So you get 0.21. Okay, next you have to estimate the approximate BOD removal efficiency. Okay, number 4, you have to refer to figure 9.8. Okay, figure 9.8. Let me find the figure for you. Appendix for trickling filters. Okay. 9.8. Where is figure 9.8? Okay, here. Okay. To identify the BOD removal, you have to refer to this table. Okay, can we go back to our example just now? Where is our example? Okay. From figure 9.8, at a loading of 1.0. Okay, since you are to find the BOD removal efficiency, definitely you have to check the BOD loading. So in this case, our BOD loading is 1.0 kg BOD per meter cube day, and from this value, from BOD loading value, you can check the removal efficiency. Any question? Any question? I think someone raised their hand. Shafika? Ada. Alright. Okay, so BOD loading in this case is equal to, let me change the colors. Okay, in this case, the BOD loading is equal to 1. Okay, so you draw a vertical line and draw a horizontal line, yeah, so that you will get the BOD efficiency. In this case, BOD removal, sorry, not BOD efficiency, BOD removal, the percentage of BOD removal is around 82%. Okay, that is how we find the BOD removal efficiency. So you have to calculate BOD loading. You have to make sure that you calculate, you have got a correct value. The wrong value of the BOD loading will give you the wrong value for the question number 4, which is the BOD removal efficiency. Okay. Question number 5, can nitrification be expected? Okay, how do we know nitrification can be expected or not? First of all, you need to know what is nitrification. Nitrification is the process of the conversion of the organic matter into nitrate. Yeah? So this is the process of adding nitrogen into water or wastewater bodies. Okay, so if the process nitrification keeps continue occurring, so that will end up having higher concentration of nitrogen. So normally, whenever nitrification occurs, it has to be completed with other process which is known as denitrification. Denitrification is the process of the removal of nitrogen from nitrate to nitrogen gas. Yeah? So we shall discuss this in detail after the semester break. Yeah? About what is nitrification and denitrification. Okay, so let's see here whether from this condition whether nitrification can be expected or not. Yeah, the answer is no. But how do we know whether it's no, yes or no? Yeah, so this can only be determined from the value. Well, definitely it has to be determined from the value. Okay, let's see. You have to refer to table 9.5. Yeah, refer to table 9.5. Let's see together 9.5 here. Okay, so in this table, we are to design, we are to check for the combined BOD removal and nitrification. We have to check for the combined BOD removal and denitrification. In this case, the BOD loading that you have calculated earlier is 1.0 and the total nitrogen is about 0.21. Okay, and you go back to the table. Okay, the table that you have to refer is this one. I put in green here. Yeah? I hope that you can see my green line here. Yeah. Okay, in this case, what is the BOD concentration just now? In our case, our BOD is 1 kg, right? Yeah, 1 kg. What is the value for the TN? Our TN is 0.21. Yeah, 0.21. So does 1 kg falls within this range? No, because the range that stated here to prove whether nitrification will occur or not, it has to be between 0.1 to 0.3. Yeah, and while for nitrogen, yeah, the value is 0.21. It does falls within this value. Nevertheless, since one of them does not fall within this value, therefore notification cannot be expected. Yeah, unless your COD is 0.2, your nitrogen is 0.21. So since both falls within this range, so notification can be expected. Okay, it has to be both parameters. It cannot be only one. Okay, any question? Any question? Tak? You understand what I mean? Do you have any question or you want me to repeat? You want me to repeat? No. Okay. Faham ke?
Boleh repeat.
Okay. Since we have calculated the BOD loading is 1 kg meter cube day, and you have calculated earlier the total nitrogen is 0.21. Question number 5, it asks you to check whether notification can be expected or not. To check whether notification can be expected, we have to refer to table 9.5. Yeah, it's given in the appendix here. Table 9.5. So which row that we need to check? Definitely the row of combined BOD and nitrification. Yeah, because we have calculated for both nitrogen as well as the BOD. Yeah. So in this case, yeah, I put in a green box here. Yeah, you have to check whether the BOD loading, yeah, that you have calculated falls within the suggested value or not, and also the total nitrogen loading falls within the suggested value or not. First, we check for the BOD loading. Your BOD loading is equal to 1.0. So the suggested range, where nitrification can occur is 0.1 to 0.3, while your value is equal to 1. So that's why it doesn't fall within this range. What does range of what? A range of 0.1 to 0.3. Yeah. So then checks for total nitrogen. Total nitrogen, the value that you calculated is 0.21. So and it does falls within this value. Yes, sebab yang atas ni, the top one is BOD, the bottom one is for nitrification, for total nitrogen. So even only one of them does not falls within the range, therefore nitrification cannot be expected. Nitrification can be expected if both of the parameters falls within the recommended range. Okay, faham tak?
Faham ke? Understood.
Okay, great. Okay, next. At the even though the total nitrogen loading is appropriate, so at the higher BOD loading, the heterotrophic bacteria outcompete the nitrifying bacteria for site on the packing surface. So this is due to the carbon to nitrogen ratio. So in this condition, the concentration of carbon is too high as compared to the nitrogen. For that reason, nitrification cannot be expected. You can see the difference in terms of the concentration. While we have BOD represented the carbon is about 1, and nitrogen represented, total nitrogen represented the nitrogen. So if we are to compare between carbon to nitrogen ratio, it's clearly even before we check the table, we know that this is at this ratio, nitrification cannot be expected because the BOD is too high as compared to the total nitrogen. Okay, number 6, what is the specific total nitrogen loading? So in this case, you have to refer to table 9.2. Where is table 9.2? Table 9.2 is here. Okay, table 9.2 is here. Let's choose pink in color. So pink 9.2. This is on physical properties of trickling filter media. Okay, let's study one by one. First, the first column. The first column. The first column is actually the packing material that we would like to use, the filter media that we would like to use. In this case is clearly mentioned in the question that conventional cross-flow plastic packing. So these are the keywords these are the keywords that tell us which row that we would like to refer in this figure. So in this case we are to refer the plastic conventional. Why? Because it's mentioned here, plastic packing. Okay, conventional cross-flow plastic packing. So you jangan pergi ambil high specific surface area ke random packing ke, unless sometimes and this question is easy because the keywords is clearly stated. The keyword is clearly stated in the question. However, to some cases, maybe the keywords is not given. You are to determine which packing material are to be used. You are to determine which packing material are to be used based on the characteristic of the wastewater. For example, if the wastewater contain high concentration of metals, high alkaline material, so maybe plastic is not suitable. Why? Because they can be affected by the corrosion. So that maybe you have to use the river rock. You have to choose the river rock. So these are the justification. Sometimes justification is required for you to decide which packing material to be used. Okay, so plastic random packing for high specific surface area. In this case, for high specific surface area, the last row, high specific surface area is good if we have very high concentration, if we are to treat high concentration of effluent, because at extreme concentration, is really required high specific surface area so that we can have more microorganism. Okay, let's complete our example here, number 6 just now. Okay, the specific surface area of the packing is 90 meter squared per meter cube. Where do I get 90 meter squared per meter cube? So in this case, okay, in this case, since we are to refer to this row, we are to refer to the row of we are going to refer to the row of plastic conventional, so that the approximate specific surface area is 90. Okay, this is where they got 90. Then you substitute into this equation. Total surface area equal to surface area. This is per meter over volume. So you will get the surface area. So this one is the specific surface area in the unit of meter per meter cube. So when you cancel out, this 90 is actually 90 per meter. So that is why you can get meter squared here. So specific TKN of equal to Q and not over A. So Q is given earlier and not is the original concentration of the nitrogen in wastewater. A is the calculated area, so you will get the specific loading. Okay, so that's all. So this is how that we can calculate the specific loading. Depends on the question. It's not necessarily asking you to measure to calculate for the BOD. We can also ask you to calculate for the TSS. You can see the difference in terms of the if we can check, we can combine the BOD. We can ask you to check for the BOD only. For the partial BOD removal or during the secondary treatment. So you have to be very careful reading the question. You have to read the question carefully because there must be some keywords available so that you can decide which row that you have to refer to solve for this question. For example, table 9.2 just now. Table 9.2 just now, you can see the application. River rock is suitable if high nitrogen concentrations. River rock large is suitable for nitrogen, carbon and nitrogen. Same goes for plastic conventional. But if you are to consider only the nitrogen, so you can see only these three, yeah, are to be used, which is river rock small, the plastic high surface area, as well as plastic random high surface area. Yeah, so you have to see the application, so then only you can decide which packing material to be used. Yeah, so sometimes in the question I can mention high nitrogen only to treat the nitrogen, or I can is good to treat for both carbon and nitrogen. Yeah, so these are the keywords, yeah, that to be used. Okay, if the organic matter, then we are referring to carbon. Yeah, the organic matter, then we are referring to carbon C. Yeah, if we mention about protein, and so that this is equal to nitrogen. Okay, carbohydrate is also carbon. Yeah, this is carbon. Yeah, organic matter, carbo. It can also exist as the carbohydrate. It can also exist as sugar. So all of these substances will contribute to carbon. However, protein, it will contribute to the nitrogen. Okay, so I think that's all for today. You have any question?
Not at
Okay,
No,
great. All right, so I'll see you in 2 weeks' time, inshallah. We will be having another series of lecture. But just to keep my words, yeah, the test will be covered only up to this week lecture. Okay, only up to this week. Anything that will be discussed in week 7 is not part of the test. Yeah, so test 1 only cover lecture 1 until lecture 6. Okay. Don't forget to fill up the attendance. Yeah, let me have a screenshot of this session. Okay, if there is no further questions, so thank you very much, everyone. After your test, I will pass to you the question for the project. Yeah, I think you do have works to do, right? You have to complete the assignment, both individual as well as the group works, kan? So please let me know if you need extra time, especially to submit the group works. I can consider you to submit in week 9 instead of week 8 if you don't have enough time to submit in week 8, so that I can allow for the extension till week 9. Yeah? Okay, with that I thank you. Eid Mubarak and have a pleasant afternoon, everyone. Bye.
Thank you, Doctor.
Thank you.
Bye.
Okay.
Okay, enjoy your holiday. Bye.